Hi, and welcome to Module 8, the last module of video lecture 4. We started off discussing what it sort of entails to compute derivatives. We learned the derivatives to 3 separate classes of functions: polynomials, exponentials, and logarithms. And we learned the 3 rules you need to use in order to compute derivatives. The fact that the derivative is a linear operator, the chain rule, and the product rule. And with those 3 types of functions and those 3 rules, we discovered that you can compute most derivatives that you ever need in political science. So in this very last module, we're going to put those things together and try to talk about general practices for taking a complex function and breaking it down such that you can compute a derivative of that complex function. Now, I should say that throughout this whole series of modules, we've been talking about the rules conceptually, how to derive them, and trying to get away from the presentation of calculus as a list of many, many rules you must memorize. That said, we do have in the textbook, listed for convenience, the rules. It's on page 130, this printing, and you can see that the rules are all listed here. These are just the rules we went through before. You don't need to memorize them, but you will over time effectively memorize them. And it's a good place to go and find them quickly if you need them. Okay, so for the rest of this, what we're going to do is start off trying to understand when to use the rules. Okay. So let's begin with a simple example. If the function you're given to differentiate is already exactly representative of one of the types of functions we've used before, you do not need any more of the rules of differentiation, right? So if you have a function that is some power of x, you can differentiate it. A simple way of thinking about this is that the derivative is just what you get when you pull down the exponent to the front and then subtract 1 from the exponent for the new exponent. And there's that derivative. There's no other rules you need to apply. Similarly, if you have e to the x, or an a to the x, but let's stick with e for now, then the derivative is e to the x. No rules need to be applied. And if the derivative is, and if the function is a logarithm, then the derivative is 1 over x. Again, no rules need to be applied. So that's good. What if you have more complex functions? Well, moving one step back, the goal is to identify these components that we just wrote down over here, to identify these components in your more complex functions. Okay. So in other words, to break down your larger function into these smaller components. Now, there are going to be lots of examples to go through in the problem sets that accompany this course. There'll be some more worked examples in the problem sessions, but I'll just give a sense of how to go about doing that in this lecture, this module. So, where do we start? Well, first thing is, if your actual function is just a sum of these components, or a difference of these components, or a sum and a difference of these components with each component multiplied by a constant, then the fact that the derivative is linear gives you all you need to know. So for instance, if your function looks like, let's see, 7x to the third plus 2 e to the x minus 7 natural log of x, all you need to know is that the derivative is linear. You can take the derivative of each of these separately and just keep track of the constant in front. So the derivative is going to be 3x squared plus 2 e to the x minus 7 1 over x. So that's a nice easy way to compute any sum or difference of functions as long as you know the components of those functions. Those should be pretty clear pretty quickly, and you won't take a lot of practice to get a hang of that. So that's the first step. Check to see if you can just split it up into a sum or difference of things you know about already. And if you can, possibly multiply by constants. But if you can, do each component separately and then add them up, multiplying by constants as appropriate, following the fact that the derivative is a linear operator. Okay. That's the first one. Okay. Second one. What if your function is a little more complex? Next, what you want to do is see if you actually kind of get the sense of the function, right? Get the sense of what the function looks like, but maybe it has some complexity to it that you're not familiar with. So for instance, the simplest example of this might be this, x plus 1 squared. Now you could go and multiply out x plus 1 squared, right? And get x squared plus 2x plus 1 and differentiate that. That's fine. But it's better to have a more general rule because maybe you have this thing. And that thing you do not want to go around multiplying out. Now you can remember the binomial expansion for this kind of thing, and that's fine. But it's still going to be a lot of terms, and there's no reason to go about doing that. Because there's an easier way to do it. If you look at this function carefully, you may think, okay, well, maybe it's actually two functions together, right? On the one hand, there's x plus 1. That's a function of x. On the other hand, there's that thing squared. What if instead we define g of x as x squared and f of x as x plus 1? Now we've split this function up into a composition of functions. And the key here is that each element of the composition, g and f, are each independently differentiable by u easily. So here, g of x, the derivative is going to be, now it's going to be u because we're going to do the chain rule, but the derivative is going to be 2u, and f prime, the derivative is going to be 1. Because we can split up this function into a composition of two functions, each of which you know how to differentiate by the power rule and the rule for exponentials and the rule for logarithms, you can then do this using the chain rule. So we can go through again and just sort of shorthand. U is going to be x plus 1 because f of x. We already have g prime of u. We already have f prime of x. G prime of f of x is going to be just 2 times x plus 1. And then you can multiply it to get the answer, but f prime is 1, so it's going to be times 1 is the answer, and it's just 2 times x plus 1. So we see, in fact, in this case, we didn't actually have to even consider the fact there's x plus 1. If we just treated x plus 1 as x and differentiate that, we'll get the same answer. Why is that? Because of the chain rule. Because the derivative of x plus 1 is 1. And anything that's a derivative of 1, you can basically treat as x when you differentiate the whole thing. So for this one, we can use the chain rule again, and it's going to end up 19 x plus 1 to the 18th. Similarly, x minus 1 or x minus 7 or whatever to the 20th, the derivative is going to be x minus 7 to the 19th times 20. These are all accomplished by using the chain rule. So if you can't just split it up into some sum of things you know about already, some sum or difference of things you know about, the next step is to try to identify if the function is a nice composition of functions that you can then apply the chain rule to. Note that in this case, the chain rule is not necessarily better, but in this case, the chain rule is definitely better, right? Multiplying out is a pain in the neck, and you could use the product rule, but that is 19 terms, and that's also a pain in the neck. The chain rule is much cleaner. The first one, you could do the product rule tool if you wanted to. So the next step, right, after checking to see if it's a sum or difference, possibly multiplied by constants, is to see if you can identify a function composition. If your complicated function is actually two simple functions, one composed of the other. We did some more examples like that before when we talked about the chain rule, and also, so one of those was the exponential. Right? So any function you want to stick in here. Right? How do we solve that? Well, this is a simpler function composed with a polynomial. We can go through and do that again, and you can do this at home. I'm not going to do the chain rule again here, but what you get, because the derivative of e to the x is e to the x again, in the exact same manner we did it before, you're going to get e to the x to the third minus 7 times the derivative of f of x, so f prime, which is going to be 3x squared. Again, this complicated derivative can be done pretty simply once we've identified that it's a composition of two functions that we can differentiate straightforwardly, a simple exponential and a polynomial. This is all we're doing. We do more things with logarithms, right? So logarithm x to the 7th minus 5x cubed plus 1. Again, is straightforward. We have g of x is just the log of x, and f of x is this polynomial. Then g prime of u is 1 over u. F prime of x is 7x to the 6th minus 15x squared. So g prime of f of x is equal to 1 over x to the 7th minus 5x to the 3rd plus 1. Then you're going to multiply that by this to get your answer. F prime over f, as we saw before when we talked about differentiating logarithms and the chain rule in that context. So that's it. That's what we do. You break it down into these components. Now there'll be times when you can't actually use function composition because it's not actually appropriate, right? It's not two functions composed of each other. It's actually the product or quotient of multiple functions, right? So if you have e to the x times 5x cubed plus 2, you look at this function, it's complicated, but you note A, it's not the sum of individual functions. Well, there's a sum in there, but it's not the sum of easy functions to deal with. Even if you were to expand upon this, you would still have this term over here, right? The second one would be easy, but the first one is still not. So it was also not a function composition. There's nothing you can plug into there. There's no g and f you can define to make that thing reduce into a nice easy g and a nice easy f. And if that's not clear to you, play around with it, think about it. Try to define a g and an f, and you'll find pretty quickly there's nothing you can do there to make that simpler. Function composition is usually pretty clear. If you look at it and you see a complicated function embedded in a simple function, that's typically an opportunity for the chain rule. It's typically an opportunity to use function composition. In this case, you can't do that. It's not a sum. It's not a composition. It's going to be the product rule. So the product rule, right? Remember, it was the derivative of this is f prime g plus fg prime. The first one's f, the second one's g. So you get this back again, and when you work with exponentials, you often get things back again. Plus e to the x times the derivative of this thing, which is going to be 15x squared. Right? And if you do this directly, you get the same answer. Here's your 2e to the x, and then this thing you have to use the product rule for, which will give you the same answer. So that's the product rule. And that's pretty much it. So you can identify first, is it some kind of sum or difference of things? So if not, is it some kind of composition of things? Can you plug in one function into another function to get your function easily? And if not, is it some product or quotient of different functions? And that's going to cover pretty much all the things you're going to need to differentiate ever. So let's do one sort of randomly chosen larger example to give you a handle on how this works in practice when you have to break down more than one step. Okay. So let's just make up a function. I'm going to call it, I'm going to run out of letters pretty quickly, so I'm going to call it the function a. Right, so let's make up a function that's decently complicated. So let's see, let's call it 3x squared plus 2x, and we'll have an e to the x squared minus 1 times logarithm of 7x cubed minus 15. And that's probably enough for now. Okay, so this one's reasonably complex. There's a lot of stuff going on here, but again, You're just going to be applying all the things you learned in sequence. So let's look at this. A few things. And let's add something to here. Okay. So let's first look what we can do here. First look for sums and differences. So we see, switch color here. Over here, here's a sum. This is a regular polynomial. There's a sum over here. There's a sum over here. These are regular polynomials, but just treat them as polynomials. But the whole first term is added to the second term over here. So in the first step, we can differentiate each term separately. So let's call this first term b of x, and the second term c of x, so that a equals b of x plus c of x. Well, now we can use the fact that the derivative is linear to do each one separately. So a prime is going to be b prime plus c prime. C prime is just 17 e to the x. The derivative of e to the x is e to the x, so that one is going to end up being 17 e to the x again. So that part we can deal with separately, put aside. So let's put that aside for now and think about, so c prime is going to be 17 e to the x, and we'll put that aside for now. Now we'll have to deal with b prime. What's b prime? There's no more sums between those two things, and the whole thing can't be reduced easily via some kind of function composition. There's nothing there you can just plug into another easy function to get a more complicated function. However, there are three elements there, right? There are three elements multiplied together. Therefore, the product rule can be used. If they were divided, you could use the quotient rule. I only have a certain amount of space in this page for now, so I didn't want to use the quotient rule, but it's the same idea. So here's three things in the product rule. Let's now call b equal to d times e times f. And what the product rule says is b prime is equal to d prime ef plus d e prime f plus d e f prime. Remember, you have one derivative in each of those terms. And there's one term for each derivative. So there we go there. Now we split it up even more. Well, d is this thing over here. This is d. Right? So d is going to equal 3x squared plus 2x. That prime, we know, it's a polynomial. We can differentiate that, and if that's still not clear to you, you'll do it by hand, write it out. Make sure you get that. That one's pretty clear. But e and f, right? So e, so that's d prime. We can dispense with d for now, and d prime. E of x is equal to e x squared minus 1. There'll be too many e's, but sorry. And f is equal to the log of 7x cubed minus 15. And we still need those derivatives, right? Part of the product rule requires e prime and f prime to get b prime, and b prime is needed for a prime, right? So we're just breaking it down bit by bit until we get smaller and smaller pieces. But now, right, now these are not products, and they're not sums. However, in each case, it's one function composed with another function. In the case of e, it's e to the x composed with x squared minus 1. And in the case of f, it's the log composed with 7x cubed minus 15. So in each case, we can use the chain rule. In the case of e, we can write e as equal to g of h of x, where g equals e to the x and h equals x squared minus 1. And in the case of f, we can write f equals I of j of x, where I of x equals the log of x, and j of x equals 7x cubed minus 15. So I've broken that down. We can find each prime separately. Again, I'm going to skip some steps because I ran out of room here. So, but again, you should do it at home, writing it down. So here, e prime is going to be e to the x squared minus 1 times, that's ex prime, just to make it clear that's not the constant e, times 2x. And this should look familiar. It's again the exponential back again, times the derivative of the thing in the exponential. That's what the chain rule always returns for exponentials. And f prime is going to be 21x squared divided by 7x cubed minus 15. Again, f prime over f, in this case, f prime over f, which again is what the derivative of a logarithm always returns. I'm missing the minus here. It's minus. Okay, and that's it. Now I'm not going to simplify this because it's a giant mass, right? But note, we can now put it all back together again, right? So first we split a into b plus c. C prime was straightforward, so we computed it. B was not so straightforward, but we can write b prime in terms of this whole thing over here using the product rule. Now we need to compute d prime, e prime, and f prime. D prime is straightforward, but we needed e and f, and they weren't straightforward. But using the chain rule, we can compute e prime and f prime, and now we can plug back in d prime and e prime and f prime into here to get b prime, then plug b prime back into here along with c prime, which is up here, to get a prime. It'll be a giant mess. I'm not promising something nice and pretty, right? But this is a giant mess. But the point is, you can do this, right? After a very short time, without even knowing what the derivative of what is, you can, in theory, sit down and differentiate that giant function on the top of that screen, right? Using just definitions of how to derive 3 functions and how to use 3 rules, all of which were derived from a single definition. So, and again, this might not be as fast as I just did it here, right? I've been doing these things for a long time, and you're quite possibly seeing this for the very first time ever, right? But the point is, this is not some mysterious secret thing that only a few people know, and if you just don't get it, you can't get it. This is something you can do by practice and getting used to identifying the ways to split up more complicated functions into simpler functions. There aren't a ton of rules to memorize. There are very few, actually. There are 3 types of functions, and 3 rules here, and that's it. And if push comes to shove, you could, in theory, rewrite the entire thing from a single definition. Now, I'm not recommending you do that, but you could, in theory, do that if you wanted to. With those rules, you can take any large function, pretty much, typically any large function you can find in political science, and split it up into smaller pieces that you can deal with, differentiate, and then build the whole derivative back up again from those component pieces. In that way, derivatives are actually pretty nice things, right? They're things you can deal with, they're things that can be broken up into smaller pieces, and you never have to just identify it all at once as some kind of whole. You can break it up into smaller pieces and deal with it. Sometimes you might encounter ones that aren't dealt with in this class, but again, most of those just involve a particular functional definition that you haven't dealt with so far, like a sine or a cosine or whatever. Right, a trigonometric function like that. But you can do it, and you get better and faster the more you practice, the more you get used to identifying first how to differentiate sums and differences. That'll be the first thing you'll figure out. And then probably the product rule will be next, and then the chain rule will probably be last to identify composition. It's a little more tricky, it takes a little more practice, but it's just practice. The more you practice, the faster and better you'll be at identifying things like function composition and product rules, and so on, and the better you'll be able to compute derivatives. Now, why would you want to do that practice, right? Well, we talked a little bit about some of the reasons why to figure out minimal error or maximal likelihood, right? Or in game theory to identify optimal behavior. The real payoff for this kind of computation will come in the lecture after next, in lecture 6, when we discuss optimization, and you'll be using these explicit rules in order to find the optimum of functions, which will let you understand what individuals' best responses are to each other, what the coefficients are that maximize likelihood or minimize mean squared error, right? Things that help you understand how to use statistical inference, to use game theory to help understand behavior and incentives in behavior. All that stuff requires that you take derivatives in order to maximize things. And here we've gone over how to do that. So take a break now. In the next lecture, before we get to the payoff of this stuff, we're going to talk about integrals. They're the opposite of derivatives. They're the opposite of derivatives. They're used less often. They're less easy to deal with in a bunch of ways. The good news is they're used much less often in the social sciences. We'll talk about what they are, when they're used, and go over how to compute them in the next lecture. Thank you very much.